This is a walkthrough of problem 2 on practice exam 2 of module 6 in the book Problem Solving Guide for Mechanics and Thermodynamics. We have a 100 gram mass and a 300 gram mass with a compressed spring between them. They are moving together at a speed of 30 centimeters per second to the right. I have a remote control that releases the spring. Ding! The masses fly apart. The spring pushes the mass apart. After it's released, the 300 gram mass moves to the right with a speed of 120 centimeters per second. It was initially going 30, the spring is released, now the 300 gram mass is going 120 centimeters per second to the right. What is the velocity of the 100 gram mass? What is this guy doing? How many millijoules of elastic potential energy were stored in the spring? There's our diagram it came with. This is a one-dimensional motion problem. It allows us to apply conservation of energy and conservation of momentum. The initial momentum in the system, you can group those two things, are moving the same speed. 400 grams, moving 30 centimeters per second to the right. That's 12,000 grams centimeters per second. Let's put that in the diagram. 12,000 grams centimeters per second. And let's make the momentum vectors bold so we don't mix them up with the velocity vectors. The final momentum of the system is the same. The spring can't add momentum. It can add energy. It can convert its elastic to kinetic. So let's put the final situation on the diagram with the second snapshot. There's the final situation. We don't know what the speed of the 100 gram mass is. We know the 300 gram mass is moving at 100 centimeters per second, 120 centimeters per second to the right. We know the total momentum of the system is conserved. The initial momentum is 12,000 grams centimeters per second to the right. That has to be the final momentum. The final momentum of the 300 gram mass, mv, 36,000 grams centimeters per second to the right. Let's put that in the diagram. What's this guy doing? If the initial momentum of the system was 12,000 to the right, this guy has 36,000 to the right. This one has to have, you tell me. So let's set the initial and final momenta equal. 12,000 is the initial. The final is 36,000 plus the momentum of the 100 gram mass after the explosion. It's minus 24,000. Let's put that on the diagram. 24,000 grams centimeters per second to the left. So we started off with 12,000 grams centimeters per second of momentum, and we ended up with 12,000 grams centimeters per second of momentum to the right. We can get the speed of the 100 gram. We don't know the speed now, but we know its momentum, and we know its mass, so we can get its speed. It's 240 centimeters per second to the right, left, so let's put that on the diagram. And let's use a big arrow because it's a big speed. Now part B. How many millijoules of elastic potential energy were stored in the spring? So we're going to get all the energies in joules, so we're going to convert the masses from grams to kilograms and the speeds from centimeters per second to meters per second. The initial kinetic energy in the system, that's 400 grams, that's 30 meters per second, so we get 0.1 is 0.018 joules. The final is the kinetic energy of the 100 and the kinetic energy of the 300. There's the 100 gram mass. 240 centimeters per second is 2.4 meters per second. We can plug in the numbers and calculate it. We get 0.288, 0.216. The total final kinetic energy is 0.504 joules. Let's put the kinetic energies in the diagram. So here, the kinetic energy initial, 0.18. Note there's no arrow on the energy. It's a scalar, it's not a vector. There's no such thing as direction when you come to energy. So those are all the energies. Those are the kinetic energies. Here we can figure out what the elastic potential energy must have been before the explosion. It's 0.504 minus 0.018, so 0.486 joules, and the question asks for millijoules. So that's 486 millijoules. Thank you.